Okay, welcome to this follow-up video for Material Science 410, where we're touching on some background information on corrosion, a topic for the spring quarter for experiment number 1. Okay, so corrosion is a natural process which converts metal or metal alloys, for example steel, into more chemically stable forms, such as metal oxides, metal hydroxides, or metal sulfides. So for example, some metal will transform into some new metal oxide with subscripts X and Y, and clearly in this sort of unbalanced equation, some source for oxygen is needed to create the metal oxide. Similarly, metals are transformed into metal hydroxides, again with some appropriate subscripts to reflect proper stoichiometry, and even sulfides are possible, so metal to metal sulfides. Okay, so again, a question at this point would be, where does the oxygen, hydroxide, or sulfur come from? And it depends on the environment or the methods applied to convert the metal into this corroded product that is the oxides, hydroxides, or sulfides. So in your experience and everyday experiences, we understand corrosion to be the gradual destruction of materials, which ultimately leads to catastrophic failure in extreme cases of the part or material in its function or in its service role. Okay, so this is a chemical and or an electrochemical reaction, typically between that metal and conditions of its environment. So some common places are in metals associated with nautical vessels or boats. Here you can see the propeller, which needs to be protected against the corrosive environment of the aquatic environment with high salinity, for example. This graphic here shows some of the sort of cycle of electrons involved in the electrochemical half reactions for the corrosion of iron to form the common rust, here shown as Fe2O3 with an .X hydrate in the formula. And we see the role of oxygen here helping us generate the oxide in that formula. And lastly, our final picture related again to the sort of effects of corrosion on a nautical vessel propeller here. Okay, so looking at that previous middle graphic, let's take a look here at what corrosion is and what are some of the main processes involved. So we know corrosion is a combination of an oxidation and a reduction set of reactions, commonly abbreviated as redox processes. Okay, and so we're going to see both oxidation and reduction half reactions to total up to the full redox process that describes how iron transforms into a rust or an oxide. Okay, so as a reminder, oxidation is a process where we register the loss of electrons. And so when we inspect the graphic, speaking for the corrosion of iron, we can see here that iron is indicated as the Fe solid in this case. And the products of this corrosion reaction show liberated electrons. So 2 electrons have been liberated as iron solid corrodes into an iron ion in this half reaction. So there's a loss of electrons from Fe solid. A reduction reaction is going to be the opposite, where we're going to see gain of electrons in that half reaction. So we're going to see the electrons before the reaction arrow, showing that they're going to combine onto a chemical species and create a new product that is reduced. Okay, so here we see that partner half reaction shown here, where oxygen plus access to protons, which are typically accessed from water or acid, allow for 4 protons and 4 electrons to combine with O2, commonly from air, or dissolved into moisture on a surface, will lead to liquid water. Okay, so this is commonly referred to as the oxygen reduction reaction, given that oxygen is transformed into water by reduction via the gain of those electrons. So, in the above process, the two half reactions are now listed here for us. We saw the oxidation half reaction showing iron, Fe solid, transformed into an aqueous iron 2 plus ion, and loss of 2 electrons from that iron 0 oxidation state in the Fe solid. And we see here a reduction reaction occurring where those electrons are ahead of the reaction arrow, and they combine with O2 and some protons from water to give us more water in the product H2O liquid here. Okay, so notice the imbalance of electrons for these two half reactions, which must total to describe the overall process. It looks like we would need twofold of the oxidation half reaction to balance for electrons in this process. So typically we do that with coefficients out front by doubling the reaction, and we now see 4 electrons liberated from 2 iron atoms in the steel, and those 4 electrons then end up used up for the oxygen reduction reaction in the bottom half reaction. Taking this to our diagram, we can now see some of the electron cycle that's happening. So we see here that the iron sample here is the sort of gray structure and cross-section, puddle of water over top, and a site for corrosion or an anodic oxidation reaction is shown right here. And this is where we expect the oxidation half reaction to be playing a role. So we see that iron produces iron 2 ion, which leaves the surface of the iron steel and locates temporarily in the water. The lost electrons transmit through the conductive medium that is the remaining iron. Okay, so we see those electrons sort of locating throughout the sea of electrons, holding all the remaining iron atoms together and moving to a different site, a cathodic site, where the reduction reaction will occur, the half reaction showing the oxidation reduction reaction. So we expect O2 from air to be playing a role at this cathodic site, and we're going to see O2 picking up those liberated electrons from that iron site and ultimately creating water. Okay, and we now know the stoichiometry that's relevant there. One oxygen molecule, an O2 gas, is going to require 4 electrons and 4 protons from the aqueous environment to give us the 2 water molecules as our product here. So the ultimately the iron 2 in aqueous environment will later also combine with oxygen to form the rust compound shown here, giving us the Fe2O3 hydrate as the product. Okay, so this process of corrosion of metals, including steel, is a very expensive process, and it takes a toll on the U.S. economy and its overall budget. Here you can see some data from 1999 and more relevant information from 2014, and how the cost of corrosion has been increasing in a lot of different industries, including utilities, transport, manufacturing, government, infrastructure, and other associated industries. So in other words, the budget toll for dealing with corrosion is near doubled in that period from 1998 through to 2014. To give you further perspective on the cost of corrosion on the U.S. economy, here you see that the corrosion costs are roughly half of what the U.S. spends on its defense budget. And so this is not an insignificant amount of money, very much a huge toll on the U.S. economy here. And so for us as material scientists in training, developing expertise and experience here with how to protect against corrosion or to manage it by other approaches is extremely valuable. And if one can kind of manipulate and solve some of the corrosion that exists in some of these industries here, you can expect that you would have large impact on companies and other kind of governmental or societal budgets that are reflected in the data here. Okay, so we see here the job of a corrosion scientist or engineer is to help control or stop corrosion often. And the typical kind of engineers or scientists that end up in this field come from various backgrounds, a lot from material science or materials engineering, physics, chemistry even, electrical engineering, civil engineering, chemical engineering, and even business and other kind of sectors are included for collaboration and other kind of ultimate implementation of the approach to deal with corrosion. Okay, so clearly a very important topic in everyday life through to high-tech industries, and chances are that you in your future careers will have to deal with corrosion in some form or another. Okay.